So before we start, let me again, well, first of all, let me do a number of logistical announcements. You should again remember that we have a midterm in this class on Tuesday, the February 25th. I have already told you about the parameters of the exam in class, so therefore 80 minutes. We'll start promptly at 9:40 and we'll end promptly at 11. There will be 20 multiple choice questions. Oh, this does not show up. There will be 20 multiple choice questions, and there it is. And 3 short answer questions on the exam. I have posted a practice that will give you some idea of how it should look like. Let's actually see if it pops up. So I may or may not use the same questions. Well, I probably will not use the same questions as on the practice, but it at least gives you a format. It also tells you the rules up front. You will be allowed a single page for notes, double-sided if you wish. So standard 8.5 by 11. You can fill it with any information you'd like, either type or write, as long as the font is such that you don't need to use optical instruments and other decoders to actually access the information, except for prescription glasses. Well, we'll sit you out, we'll spread you out. Please bring your student ID. We may randomly sample to look out for ringers. This usually doesn't happen in this class, but it's a university policy. And I think that's about it. The exam covers what we have covered so far in the homeworks and discussion sections there for chapters 1 through 4. In other words, the information in the first 4 weeks, ending with radioactivity, but not including what we are talking about today and on Tuesday, which is the nuclear power and nuclear weapons. That will wait until the second midterm in April. So again, chapters 1 through 4, and the format is simple. And you can look at this practice for types of questions that can be asked. For example, list 3 possible alternative fuels to fossil fuels, discuss pros and cons. I would expect a relatively short answer, something that fits into a couple of inches of space. So in other words, a short paragraph, 3 to 4 sentences, concise and to the point. And there will be 3 of those. So that's essentially it. No long essays. We will have an essay on the final, perhaps. Do you guys have any questions about logistics? So take a look. This file is posted on the exams, files and exams on B courses. So in the meantime, what we were talking about on Tuesday are the issues of nuclear power. So again, let me pause before I start on my spiel. See if you have any questions. Urgent questions about this topic, previous topics, anything that you would like to ask. Yeah.
Is the hypothesis, like how many people will die from cancer, or how many people will
That's a good question. It's technically, actually, yeah, so the question was whether the linear hypothesis is how many deaths or how many extra cancers would be observed. The actual number is how many extra cancers. So, and in some sense, it's a conservative estimate. Each cancer is a tragedy. Each death is a tragedy. The actual death toll would depend on mortality of the cancers. So the upper, the most conservative estimate is that eventually everybody who will have this kind of a cancer will die. That's not true. For example, thyroid cancers are relatively, if observed and treated early, thyroid cancers have about 95% chance of survival. Obviously, other types of cancers, brain tumors, are more difficult to treat, pancreatic and other cancers too. So mortality depends on the type of cancer, but this rate just integrates over the all kinds. So in some sense, it's a conservative estimate of what the effect would be. So if you assume that every cancer leads to eventual death, this would be again an upper estimate of fatal outcomes after radiation exposure. And again, the other part about linear hypothesis that we talked about is, well, where sort of you need to know two facts about it. One is, where does the data come from? Data come from an experiment, effectively, which the American government has performed. Well, the Japanese collaborated with unwillingly. This is from Hiroshima and Nagasaki. So the exposure to radiation of survivals of the initial blasts in Hiroshima and Nagasaki, and so their excess cancers compared to the average population in Japan could have been computed since the exposures were relatively high. So these are doses per person of about 140 rem, is about 50 times larger than a typical exposure per year of a comparable human in the same area. So 500 times larger, you can see the size of the uncertainty. This is basically a statistical spread. Even though, so this person would have received 140 rem dose, increases the extra chance of cancers by 5 to 6%. There's a natural statistical spread in that. You have to count people who actually have been diagnosed, and then subtract the number of people who naturally would be diagnosed with cancers, which is over a quarter of the population. And so the fact that the sample was relatively small in numbers determines the size of the uncertainty. What this one bar is, in statistical sense, is so-called 68% confidence level interval. What it means is that 68% of people had extra cancer rates. Let's say if the exposure was 140 rem, 68% of those people with 140 rem exposure would have an increase in their chance of receiving cancers between 4 and 8%. This is the size of the uncertainty. So what happened to the other 30%? Well, some of them had perhaps a higher chance of cancer, some of them had lower chance of cancers. So again, this data is somewhat limited by the size of both by the size of the effect, by the actual exposure, and by the size of the population sampled. But this is the best data we have. We obviously don't want to expose normal humans to small doses of radiation. That's unethical. When they expose rats, but then you have to extrapolate, and the biology is different, somewhat. Most rats die of cancer. Well, the typical lifespan of a rat is 2 years, and most of them actually do die of cancer. So, one can, expose them to radiation, talk about ethical or unethical process, but it still would be difficult to extrapolate their biology to ours. You have to make some assumptions. So this is the best data we have. In particular, there's no data at low end. And this is, again, where the linear no threshold versus threshold debate comes in. Linear no threshold hypothesis is the most conservative in two ways. One, it's an extra chance of cancers, and you can assume, for again being conservative, that it ultimately leads to mortality. And the second conservative estimate is the fact that you assume that no matter how little the radiation exposure is, your chances of getting a cancer increases. We don't have any data for any exposures below about 5 rem, which is 10 times or more than 10 times the average annual dose a typical human receives. So what happens at low end is, in some sense, again, a hypothesis, an estimate. And the most conservative estimate from the point of view of protecting the public is to assume that no amount of radiation is safe. Whether this is true or not is subject to debate. One can make models where small amounts of radiation can be recovered, reprocessed by the body. One can make arguments that maybe a little bit is good for you, it increases mutation rates, and maybe that's fine too. Who knows? We have no data. And so various proponents of various advocates of either pro-nuclear power, for example, or anti-nuclear power can make arguments based on the same data and reach different conclusions, depending on what you assume happens here. So it's also important to understand. So those debates then become basically policy debates rather than scientific debates. Science data is here. Do you guys have any other questions? We'll come back to this graph. So we have talked about nuclear fallout. I think where we stopped is the proliferation issues. And again, discussing policy is sort of part of this class. I will try not to give my opinion here. That's not my role, although you can guess sometimes. It's something that you are welcome to discuss in class, in the discussion sections, or even after class with me if you wish. The issues of nuclear proliferation clearly affect the entire human race, or may potentially affect the entire human race. And again, there are arguments pro and against. If you're a country which has 10,000 nuclear weapons like the United States and Russia, you would argue against nuclear proliferation, clearly. You would like to own UN plus your 5 favorite bodies that have signed the treaty, would argue against nuclear proliferation because you would like to, A, maintain dominance. This is nuclear weapons are a deterrent against using nuclear weapons. And it's also a deterrent against using conventional weapons in the normal conventional warfare. There's always a risk that if, let's say, I know, suppose China attacks the United States or the other way around, each country knows that in case of a standard, regular military confrontation, there's always a chance the other country, if they're pushed to the brink, may use a nuclear weapon technology and therefore annihilate the other country. The same is between Russia and the United States. So this acts as a deterrent against both using nuclear weapons and using conventional weapons when confronting a military that's similarly equipped. If a small country, I know, pick one, North Korea, which may or may not have 10 weapons, which may or may not be ready to fly yet. North Korea has 1 million soldier army, roughly, ready to strike South Korea. I mean, the doctrine be what it is. They are ready to defend their turf. They also, after the Korean War, ready to reclaim the rest of the peninsula. In principle, they've been deterred by the fact that in the case of that confrontation, the United States would come to the aid of South Korea with potential for using lethal nuclear force. So that's a deterrent. If you're a small country like North Korea, you would like to obtain nuclear weapons, therefore you're pro-proliferation. You would like somebody to give you the technology, or you would like to be able to buy the technology, or you would like to be able to steal the technology, but somehow you'd like to be able to develop the technology, again, to provide deterrent for your enemies. So North Korea, well, being perhaps paranoid as they are, and somewhat enclosed country, may want to, they have 1 million soldier military, but it would have been more, perhaps cheaper for them to use the nuclear weapons as a deterrent against attacks by the imperialist peaks from the United States, as they would call them, or as the Soviet Union would call Americans 20 years ago. So they are trying to develop this, and the same with Pakistan and India, who even fought, who are not the best of friends. They develop nuclear capabilities exactly as a deterrent against the other, their typical mortal enemy. So whether spreading nuclear weaponry is good or bad for world peace and stability is an interesting subject for debate. As I mentioned, there are theories that postulate that since it works so well for United States and Soviet Union, there has not been a World War III, knock on wood, since 1945. There have not been an all-out world war. Yes, United States fought in Korea, and yes, there were some Russian advisors, and there was even Chinese military there. Yes, United States fought in Vietnam, and there were Soviet military advisors there. Yes, Soviet Union fought in Afghanistan, and United States supplied weapons to Mujahideen, but there was no direct confrontation between United States and Russia. And part of the reasons is the 10,000 warheads on each side. So since this deterrent works so well for United States and Soviet Union, why not, some argue, these guys, spread the wealth around, and then everybody has a big stick. And if you know, if you walk in the street and everybody's walking with a big stick, you may not be inclined to use your big stick against them. Perhaps this argument has some merit, except that then you have to think about, what happens to a crazy person who also carries a big stick. So the spread of weapons to unstable regimes becomes potentially destabilizing as opposed to stabilizing. So again, this is not science in some sense. Science can tell you what happens if we were to drop a weapon in a populated area, or a terrorist were to drop a weapon in a populated area. This is what happens. The policy question becomes is what do you do to A, prevent this, B, save the population outside of the directly affected area in case of this disaster. Well, and then C, obviously, what do you do to prevent spread of this technology to rogue nations and rogue regimes and also terrorist organizations. We'll get back to what the countries actually already do. Israel is a few hundred kilometers away from Iran. Iran has declared that Israel is their mortal enemy and shouldn't exist. Iran is said to be developing nuclear technology. That's not that great for Israel. So what should Israel do? Should they attack before Iran has had a chance to develop nuclear weapons? Should they use sabotage to prevent Iran from developing nuclear weapons? Sabotage is an act of war. Again, it becomes a policy question. So these tables list the current arsenals. Of course, we've discussed the fact that nuclear weapons are not that easy to build for a third world country, and that's perhaps a good thing. On at least 5 countries have developed large arsenals. They're all large-size industrial countries, and there are 2 reasons for that. Uranium bomb, the uranium, there was a model of this uranium gun style design is relatively easy to design and build, but requires enriched uranium. Plutonium bomb is a little bit more technologically challenging, requires less of the fission material, but still requires enriched plutonium. So if you're building a fission bomb, you typically need a large amount of fissionable material, somewhere in the range of 10 kilograms of plutonium and 30 to 50 kilograms of uranium, and you need it enriched to 80 to 90%. Natural uranium, so uranium is here in the periodic table, and you can see the atomic number here is 238. Most of the naturally occurring uranium that has lifetime, half-life of 5 billion years or so is uranium-238. About 0.7% of it is uranium-235. Uranium-235 half-life is significantly short, and so it's been decayed. It's decaying away. So if you want to build a bomb, you need to start with natural uranium, have tons of it, and then get rid of most of the uranium-238 and try to extract about most of the uranium-235, starting with about less than 1%, and increasing that density, increasing the concentration to 80 to 90%. So in other words, if you start with 1 metric ton of normal uranium, it has 0.7% of uranium-235, that's 70 kilograms. That's enough for 1 bomb. But now you need to take that 1 ton and process it to make enough for a single weapon. And that's not easy. On the other hand, if you're operating nuclear reactors, you actually don't need, we'll discuss how nuclear reactors work later today. Nuclear reactors need some enriched material as well, but at a much lower concentrations. In fact, there are some reactors that are designed to operate with natural uranium, that's mostly uranium-238, burning the however little of uranium-235 is in there. The standard reactors operating in the US, so-called light water reactors, and in Japan, require some enrichment, but again, at the level of only 3 to 5%, that's 20, 30 times slower than the weapon-grade uranium. So this is easier, clearly. And so many more countries than the United States and Soviet Union have developed nuclear reactor technologies or have bought nuclear reactor technologies. For example, Iran is buying those reactors from Russia and used to buy them from France. And they claim that those nuclear reactors are purely for peaceful purposes, for the purposes of nuclear power and nuclear research. On the other hand, they have these plans. I've showed you this photograph before. This is Mahmoud Ahmadinejad, who used to be the president of Iran until last year. This is him, a nice-looking gentleman, touring the Iranian nuclear enrichment facility. These big columns here are so-called centrifuges that take natural uranium, convert it into uranium hexafluoride gas, and enrich the fraction of uranium-235 from natural abundance of about 0.7% to higher number. And how high you need to go depends on the use for this fuel. If you are trying to build up enough fuel to run a nuclear power plant, you only need several tons of uranium enriched to 3%. If you're trying to build a bomb, you're going to get to 80 to 90%. If you're doing medical tests, maybe you can get away with 20% or so. This is what Iranians claim. They claim that they build the centrifuges to get enough enriched uranium for medical facilities. And one can argue how honest that statement is. But this is how the centrifuges work. So there are actually 3 types of enrichment facilities. The centrifuges is the most common. It's kind of easiest to make. What happens is you take uranium ore, so-called yellow cake. It's yellow because that's what the uranium looks like. You convert it into a gas called uranium hexafluoride. It's uranium plus 6 molecules of fluorine, fluorine here. And so this gas will have most of it containing uranium-238. And so the molecular weight of that molecule with uranium-238 is 238 nucleons of uranium plus 6 nuclei of fluorine. So that's 6 times 20 roughly is 120. So molecular weight is, what are we talking about, 240 plus 120, 500 or so, 520. And then small fraction of these molecules will have slightly lower weight by 3 units. So we start with 500 units of uranium hexafluoride. If it has uranium-238, if you put uranium-235 in there, the molecular weight is 3 units lower. That's less than 1%. So the uranium you're trying to pull out weighs about 1% less than uranium that you're trying to get rid of. So then what you do is you put this in the centrifuge, and you spin the centrifuge very quickly. And so you guys know, you've seen Professor Bob Jacobson here doing a demo with somebody, pulling, sitting on a little centrifuge in a rotating chair, pulling the dumbbells in and out. If you watch Olympics, you know how the skaters spin themselves fast by pulling their arms tightly in and then slow themselves down by pushing the arms outwards. This is the concept of angular momentum. The fact that, if you are on a merry-go-round, you feel the same thing too. If you're driving a car, you bank sharply, you feel yourself being pulled to the outside by your inertia, or so-called centrifugal force. And this force is larger the heavier the element is, or the heavier the person is. If you weigh 200 pounds, you experience the force that will be stronger to the outside than than your passenger if they weigh, say, 100 pounds. So the heavier elements, when you spin them in the centrifuge, tend to be pulled to the outside, and the lighter elements tend to stay inside. So the gas separates. And so you have the enriched uranium that's, so this, heavier stuff tends to be on the outside. The enriched uranium tends to sit closer to the center and can be extracted through the gas pipes to the another container. Now, the problem with this process is that it's extremely slow. Effectively, what you're trying to do is you're trying to separate two molecules whose weight is only different by about 1%. And there's natural mixture, there's convection currents, and they mix these elements together. So the centrifuge is spinning quickly, it's trying to separate the two elements, but temperature, and the thermal convection currents are trying to mix them back up. Each process, each stage typically can increase the enrichment by sort of on the order of 1%. So now you're trying to get from 1% to 80%. This process requires multiple steps. And so that's why you have these enrichment facilities arranged in rows. So one centrifuge feeds another centrifuge that feeds another and another and another. In this process, each step can increase the enrichment by sort of on the order of %. And so you keep going until you get your desired concentration. And if you're weaponizing uranium, that's 80% or so. And you need to do this on industrial scales. If you try to make one warhead, you need 50 kilos of uranium. And so you start with a ton of uranium yellow cake. You don't convert it into a gas. Gas density is relatively small. You're starting with a ton of gas that occupies very large volume, cubic meters or thousands of cubic meters. And then you keep feeding those thousands of cubic meters to a chain of the centrifuges. Requires an industrial size plant, sort of a size of a small or large warehouse. And you can sort of see this, these guys have built one. Again, but still slow process, requires a lot of power, requires some good engineering. You don't want this gas to leak out. Oh, it's somewhat radioactive, that's bad. Hexafluorides are kind of nasty to start with. But even more importantly, if you allow this gas to leak out, now all of your carefully enriched uranium mixes in with either air or mixes in with the normal natural uranium, and you have to start all over again. So difficult process. So Iranians have this running. Some estimates now estimate that they could have reached levels of enrichment of 10 to 20% by now. Not quite enough to build a bomb, significantly higher than what is needed for nuclear power, so they're somewhere in between. And they claim they need it for producing medical isotopes for medical procedures. So how does one stop them? Well, one can negotiate, and that's obviously the diplomacy sometimes works. International pressure works. It has worked in other countries, like these countries listed here have started, and then since dropped their nuclear weapon programs. In fact, South Africa have in fact dismantled the 3 warheads that they actually produced. So diplomacy works. One can argue how well diplomacy works with a country like Iran, but again, that's a diplomacy and a policy issue. Well, you know, if you are, you know, if you know that, so suppose you are in Israel and you know that Iranians are just about to get enough uranium to make a bomb, then you have a decision to make. You can try to bomb the facility. Iranians, of course, know about this. One of their facilities is deep underground in the mountains, under about a kilometer of rock, so difficult to bomb. Plus, bombing is an act of war, and again, from the policy point of view, you have to judge whether, you know, an outright act of war in this case is warranted. So sometimes other means are employed. You know, nobody has obviously admitted to this going on, but this uranium enrichment facility in Iran has had terrible run of luck. You may have heard about this, I think it was called Stax virus. There was a virus that infected, industrial scale virus that infected the industrial facilities in Iran and basically ground them to a halt. Where the virus came from, who knows? There was a power outage. Somebody cut a cable. This thing requires power. Something happened to a cable. I mean, it's not a cable like this. It's a bus, you know, that runs possibly megawatts of power to the site. Something happened to that cable. It kind of got cut and destroyed. Who did this? I mean, probably wasn't some, you know, farmer nearby. Something tends to happen to this facility. You know, cutting the power to centrifuges is a bad thing. They don't stop smoothly. They can be destroyed if you abruptly cut power. Gas can leak. It's not a good thing. So they haven't been successful, Iranians, in producing enough uranium yet, and some of that potentially is because the other countries oppose the process, either by diplomacy or by other means. Of course, nobody has admitted to be doing sabotage in this, you know, in Iran, because sabotage is again an act of war. So perhaps they just had terrible run of luck with the industrial complex. So again, what to do with the country that is on an active path towards obtaining nuclear weapons is again a question for diplomacy, is a question for policy, international policy. Now, a more peaceful, actually, let me stop here for a few seconds, see if you guys have any questions about nukes. All right, we'll proceed. I showed you this picture before, right? This is the warm blue glow of nuclear power, Cherenkov radiation from the reactor core near UC Davis, actually in Sacramento. This research nuclear reactor, relatively low power, is used for producing medical isotopes. It's used for irradiating semiconductors, producing novel devices. We actually use that for those purposes as well. Nuclear reactors is an example of peaceful use of nuclear power under the conditions that are well controlled. If you're building a bomb, what you want for the bomb is to explode quickly, so it releases all of the energy in a microsecond. All of the energy being released quickly causes gases around the bomb site to heat up, explode, and catch on fire. Radiation debris by that large shockwave pressure is spread around the nuclear explosion site. If you want destruction, you want all of the energy to be released quickly to produce a big shockwave. If you don't want destruction, you want to take exactly the same amount of energy or similar or even large amounts of energy, but spread it over time significantly so that the amount of power is constant but slow enough that it can be controlled. And so nuclear reactors work under those conditions. They run nuclear chain reaction under the condition where no chain is actually created, so-called critical process where the criticality is exactly 1, which means that for every neutron produced in a nuclear reaction, for every neutron absorbed rather in nuclear reaction, exactly 1 neutron is released so that the reaction rate is kept constant. And these are the best ideal conditions for operating a nuclear power plant where the power output, thermal power output of a reactor is constant, and you can collect it, convert it to steam, and then later convert it to electrical energy. So this is what you want, constant power over time. So nuclear reactors operate under the controlled nuclear fusion. They typically use slow neutrons. If you remember, the chain reaction rule is the picture is the nuclear fission is stimulated by neutron, which breaks up a nucleus of uranium-235 or plutonium-239, and that breakup releases energy and releases more neutrons. Well, so the first step is absorption of that neutron. In a nuclear weapon, those neutrons are fast. That is, they travel with the high velocity, not high compared to the speed of light, but high compared to normal thermal motion of atoms and molecules. Those are neutrons that are produced directly in the decay. As it turns out, the probability to absorb that fast neutron isn't actually very high for uranium, and that's why you need a condensed, dense sphere of uranium to sustain a chain reaction. You need the critical mass of uranium. As it turns out, the probability to absorb this neutron is significantly higher if the neutrons are slow. Basically, they don't travel very fast. They kind of rattle around the uranium fuel, and they have a higher probability of being absorbed and stimulate the reaction. So if you take the neutron produced in the nuclear fusion and somehow slow it down, the reaction probability increases, and therefore you don't need such a dense core of uranium to sustain the reaction. You don't need enriched uranium. You can kind of separate your uranium assemblies far enough away from each other so that they don't spontaneously explode. And you can use low enrichment. So reactors typically still use uranium-235, but enriched to the level of a few percent, which is significantly easier. So how does one slow down neutrons? Neutrons are neutral particles. They don't interact with materials very well, except for kind of bounces similar to billiard balls bouncing on a billiard pool snooker's table. Depending on your country, you call it differently. So in particular, neutrons, their weight, the neutrons weigh about the same as the proton, as the hydrogen nucleus. Neutrons bounce off most efficiently off of hydrogen. They have exactly the same mass, so they behave exactly like billiard balls on a billiard pool table. They can collide with the hydrogen nuclei, protons, and in each collision leave energy, about on average half of the energy, to that hydrogen. So the easiest way to slow neutrons down is to immerse your nuclear reactor in water. Water acts as both a moderator and it provides cooling. That's very convenient. So neutrons bounce around in water, knock on the hydrogens in water. Water is made out of 2 atoms of hydrogen and 1 atom of oxygen. Oxygen doesn't do much, but hydrogen can slow neutrons down until their temperature is about the same as the temperature of the water pool. They're so-called thermal neutrons, and those neutrons are easily absorbed. Now you want to control this reaction. And this reaction, if you don't have enough water in the reactor somehow, maybe the neutrons don't slow down as effectively, you may want to speed the reaction process up. Or there may be some conditions where the reactor power goes up too much, criticality reaches slightly above 1, and you want to slow it down. That condition, that criticality, the condition that you produce exactly 1 neutron, is not stable necessarily. You want to be able to control it. You want to be able to dial in the reaction rate so that the amount of power output stays constant. You want to so-called feedback. In other words, measure the reactor power. If it grows too quickly, too fast, too high, you want to slow the reaction down, remove neutrons from the environment. And if there are not enough neutrons to sustain the reactor power, you want to increase the power. So these reactors use so-called neutron absorbers, materials that can actually capture and absorb neutrons and then transform the nucleus into some other kind with very high efficiency. So elements such as boron and cadmium, boron is here, boron is actually most widely used, and cadmium is another element, absorb neutrons very quickly, very efficiently. And so if you build a rod made of boron, or that has boron in it, you can insert into a reactor core, it will eat up the neutrons and slow the reaction rate down. Or you can pull that rod out and then increase the reaction rate. So in a typical nuclear power plant, these control rods, so-called control rods, are inserted maybe halfway, or some fraction of them are inserted into reactor core. And then by adding more control rods, you can slow the reaction rate down, or by withdrawing some rods, you can speed it back up. And so by playing with them, you can maintain the constant rate. So what are the types of reactors? Well, one is the most commonly used nuclear power plant reactor is the so-called light water reactor. There are two types. PWRs, that stand for pressurized water reactor, and BWR, that stands for boiling water reactor. This type of reactors, the pressurized water, are most commonly used in the US. Boiling water reactors are most often found in Japan. Both of those use low-grade enriched uranium, enriched to about 3 to 5%, and they differ slightly in their design. So in both cases, the medium that absorbs energy from the nuclear reaction and produces electricity is water. Ultimately, you want to convert that power into electricity, and the easiest way to do it is to run a turbine we'll talk about how turbine works probably in 2 weeks when we discuss electricity. But you have seen perhaps hand generators. Turbines, electrical turbines, use the some yoke and the kind of a transformer circuit spinning in a magnetic field to produce electricity. You need to spin the turbine. And so you can spin it by producing steam that's evaporated from a water pool, delivered to the turbine. The steam pressure will spin the turbine, and the turbine will produce electricity. So the normal pressurized water reactors have 3 loops that run the water for 3 different purposes. The inside loop that actually comes in contact with the nuclear fuel rods and therefore has a potential of being contaminated by radioactivity is contained in the first containment zone and is kept under pressure. It's circulated through the reactor core, and it primarily works as both the moderator to slow the neutrons down and to actually increase the reaction rate, and it also used to cool the reactor core to remove energy from it. So this water is superheated, it's under high pressure, is then passed through a secondary loop. In this secondary loop, this water now is at a temperature that's higher than normal boiling point of water of 100 degrees C. So this hot water warms up the secondary loop, boils the water in the secondary loop, produces steam, and that steam is delivered to the turbine, which applies pressure and converts the pressure of the steam into the rotation of the turbine, producing electricity. This is also a closed loop. Ultimately, the steam is recondensed and then piped back into the steam generation circuit. So how do you condense it? Well, in order to condense steam, you need to cool it down as well, and so you need to provide cooling to the secondary system, and that cooling comes from the condenser line that's ultimately connected to the outside. So this loop can be connected to the outside environment this loop is separated by one loop, at least from the primary loop that runs through the reactor core, and so this is a relatively safe design. A leak in this loop does not directly contaminate the loop that may be connected to the environment. The other thing that you notice is that there's a lot of water running. So that's one of the reasons that you always see nuclear power plants near big water pools or near big bodies of water, either the oceans, like in California. There's a power plant in Diablo Canyon right on the shore in San Luis Obispo. There used to be one where there's still a reactor building, but the power plant is no longer operating in San Onofre near San Diego. There are reactors in the Midwest near Great Lakes. You always need a relatively large body of water to cool the large amount of power, gigawatts of power produced by these plants. In Japan, Japan uses a modification of this. So there are pros and cons of this design. This design runs the primary circuit under pressure. And so therefore, the containment vessel that contains the nuclear core has to withstand that pressure of tens of atmospheres potentially. And so it has to be robust, it has to be well designed, it has to be inspected periodically for corrosion and fatigue, etc. So the engineering design of this vessel is relatively sophisticated. So on the other hand, if you use a boiling water design where the water boils under the normal atmospheric pressure, then this containment vessel doesn't have to be, it only has to contain radiation, but does not have to withstand excess pressure, and therefore the engineering design is a little bit simpler. So this is the Japanese design. They run the single circuit that passes water through the reactor core, that moderates neutrons, providing sustained nuclear reaction, cools it, and at the same time, this water is allowed to evaporate, can be converted into steam that then is directly impinging on the turbine. And then the loop is closed, and then the steam that runs the turbine is recondensed into water, and the loop is closed. And the energy needed to recondense the steam is absorbed and relieved by the secondary line that's now connected to the environment, to some outside water pool. So there are advantages and disadvantages of this design. The advantage is that the containment vessel here is much simpler, doesn't have to hold at more than atmospheric pressure. It only has to contain radioactivity. But on the other hand, the water that passes through the turbine is potentially contaminated by the fission-produced isotopes. And so the turbine will probably be contaminated as well, whereas in this plan, if everything goes well, in the pressurized system, the turbine can be clean. So plus also a leak in the containment vessel in the boiling water design can potentially contaminate there's one step, this loop is one step closer to the condenser loop that's potentially connected to the environment. So you have to make sure that there are no leaks between this loop and this loop. In the pressurized design, there's one extra loop in between, and so that's possibly a little bit safer. As it turns out, actually one important point about nuclear reactors. Can reactors explode if, let's say, water leaks out? I mean, you've heard about the Fukushima incident. You've heard, we will talk about Fukushima and Chernobyl. The primary cause of Fukushima disaster was water was allowed to leak out of the reactor core, exposing the fuel rods to air. Could this result in a nuclear explosion? Do you guys know? I mean, people talk about nuclear meltdown. Is nuclear meltdown a nuclear explosion? Yeah? That's right. So the answer is that when the water leaks out, water serves two purposes. It removes heat, but at the same time, it slows neutrons down and actually allows neutrons to be captured by uranium, that sustains the nuclear reaction. So these reactors are inherently safe from the nuclear explosion point of view. If water leaks out, if some accident happens and water leaks, the reaction stops. Now the chain reaction stops, the nuclear reaction stops, the nuclear decay still go. There's still fission material that has relatively short lifetimes that are produced as the nuclear reactions proceed. So there's still some energy produced by the reactor cores, but there's no possibility for nuclear explosion for a chain reaction to start. So these nuclear reactors are safe from, again, the point of view of nuclear explosion, don't work like bombs. They don't have enough material in one spot to cause a nuclear weapon-like explosion, but there's still a lot of energy produced, and so it's important to keep these cores cool so that no chemical explosion is possible, so that they don't overheat, they don't catch on fire, or they don't cause an explosion of some other gas, like hydrogen. But at least from the point of view, at least these reactors cannot be used as nuclear, honest-to-goodness nuclear weapons in the sense of nuclear explosions. There's another design. Our Canadian friends up north have this ingenious design called CANDU, that stands for Canadian Deuterium Uranium Reactor, that uses deuterium oxide, otherwise known as heavy water, as a moderator. One of the main reasons to do it is that, as it turns out, normal water contains just a normal hydrogen. Hydrogens like to bind with neutrons, forming deuterium, heavy hydrogen. So normal water actually absorbs neutrons. And it doesn't just slow them down, it also absorbs neutrons, producing a different nucleus. So that's one of the reasons why the normal nuclear reactors actually need enrichment. You need to have enough fusion materials to produce enough neutrons so that you can lose some of them to be absorbed in water. Deuterium, on the other hand, does not absorb neutrons nearly as fast. It can still absorb a neutron producing tritium, but that probability is small compared to the probability to absorb a neutron into hydrogen. So the design of the CANDU reactor is very similar to the standard boiling, actually the pressurized water reactor as in the US. It's sort of very similar in design to this, except the moderator is heavy water. And since moderator is heavy water, the steam is produced from the regular water, and then the cooling loop is also regular water. Since the moderator is heavy water, it does not stop neutrons, doesn't slow down neutrons as efficiently as water, but it still does a decent enough job. But the main advantage, it does not remove neutrons from the nuclear reactions, and therefore you can use less enrichment. Canadians started building these reactors relatively soon after the war. They did not have enrichment facilities at the time. They didn't have nuclear weapons program. And so they built this reactor so that they could operate with normal levels of enrichment. There's actually another advantage for these CANDU reactors, and that in fact sometimes causes proliferation concerns. Canadians have exported this type of a design to other countries like China and India. And there are sometimes concerns because it's actually this type of a reactor, first of all, allows one to operate the reactor with other types of fuel, not just uranium, but it also allows relatively easy access to the reactor core. The design allows to refuel the reactor, to pull out some of the fuel rods in and out of the reactor core while the reactor is still running. So it's convenient. It increases the lifetime of the reactor. In the US, a nuclear reactor, one of the cores typically stops sort of once every few years for refuel. So if you have a nuclear power plant and let's say it has 4 reactor cores, chances are one of them is usually down at any given time, down for refueling. So the efficiency of the reactor is no higher than the efficiency of the power plant, is no higher than about 75%. because one reactor is often shut down for maintenance and refueling. These CANDU reactors can basically be run continuously, and you can just swap fuel rods in and out as you wish. But also it allows one to access these reactors at a time where perhaps the operation is not monitored. So if you are doing something illicit, like if you're trying to use these reactors to produce weapon-grade plutonium, you can, getting the plutonium out of a normal reactor is usually a big operation. It's easier to notice for somebody who's monitoring your site, for example, the World Nuclear Regulatory Commission monitors nuclear power plants and their operation, and they would notice if you stopped the reactor to pull the fuel rods out, they can actually look at what happened to those fuel rods. If you have a very easy access to the reactor and you can pull the rods in and out easily, it also allows you to somehow bypass those security measures. So there are some concerns about proliferation with this type of reactors. And now the last very unfortunate design that's now infamous is so-called RBMK. This is the Soviet era design. RBMK stands for, it's actually a transliteration from Cyrillic. It's actually called RBMK, реактор большой мощности канальный in Russian, which in English it stands for reactor of high power channel type. It actually uses different material to moderate neutrons. It uses graphite. Graphite is basically carbon. You have it in your pencils. It uses graphite assemblies to slow neutrons down. And then it uses water to remove power, to remove energy from the reactor core, and then ultimately boil it and produce electricity. So it sort of separates the functionality. Carbon moderates, water removes energy. And water also slows down neutrons too, but it has a secondary, it's of secondary importance in this design. So there are sort of arguments about why this design was put forward. The one thing about this design is that if it operates under normal conditions, it was designed to be very safe and easily computer controlled. Computer controlled easily on sort of 1980s standards. It's also, the reactor core also can be accessed while the reactor is in operation, and so some would say that this was designed for, again, easy access to plutonium that's being produced in the reactor core. So one could argue that this was the design that made it easier to produce weapon-grade plutonium for the Soviet weapons program. It also has a relatively light containment system. It does not, water does not run under pressure, and so the containment system is relatively easy to engineer. So the main feature of this reactor is it was cheap. And so large quantities could be produced. And in fact, there were, I believe, over a dozen nuclear power plants in Soviet time that operated with this design. The first one was built near my hometown in St. Petersburg, and it's still operating. And Chernobyl used this RBMK design. Now, as it turns out, this design had a fatal flaw. The fact that the two different moderators were used, the carbon, the graphite was used as a moderator, and water was used effectively as a secondary moderator. It had only about a 10% effect. As it turns out, this design was subject to, under certain conditions, very far outside of the normal operating parameters of the reactor. At low powers, the reactor was unstable. And so, this was actually known to reactor designers, and so reactor designers published a manual that said, under no circumstances should you run this reactor at low power. There was a limit of about 700 megawatt limit for a reactor of the Chernobyl type. And so if you're normally producing electrical power, that's fine. You're running this reactor at a typical thermal power output of about 3 gigawatts. And so chances of that power dropping to 25% of its normal capacity, 700 megawatts or so are small. You can make sure this doesn't happen by computer control, by human intervention, and so forth. You can design safety features into the reactors that would prevent it from these runaway conditions. But if you operate at a very low powers, at the powers that actually were observed in the Chernobyl accident of tens or about 30 megawatts or so that's few percent of its normal capacity, it was subject to a runaway conditions where the power outputs could fluctuate wildly. And that has to do with the water boiling. In fact, boiling water in these reactors would in fact increase the production of neutrons because the water nominally absorbs neutrons, and water steam has a much lower density, does not absorb neutrons as efficiently. So we'll get to that accident when we discuss Chernobyl accident, perhaps next week. Well, we'll see how we go today. So what are the advantages of nuclear power? Well, clearly, it's if you go back to amount of energy produced per gram of uranium, it's 1,000,000 times larger than a typical energy produced by fossil fuels. So nuclear reactors have a distinct advantage in that you don't need as much fuel to produce a large amounts of power. A typical nuclear power plant has a core that can produce of the order of a gigawatt of electrical power per reactor core, and at the efficiency of 30% or so it typically operates at a thermal power of 2 or 3 gigawatts. The amount of uranium needed for this is relatively small. So in fact, if you look at the amount of uranium in the Earth is sufficient to operate to satisfy the entire energy needs of humankind for hundreds of years. And even essentially infinitely, because these reactors, uranium-run reactors, also produce plutonium, plutonium-239, that can actually be extracted and used as fuel in another reactor. And so if you actually allow for that process to happen, then the supplies of energy are essentially infinite, well, given our extrapolated energy needs into the future. The power is relatively cheap. So here are some of the costs. If you can actually access public documents about how much Diablo Canyon nuclear power plant cost to build. It's roughly $1 billion per reactor core, so per about gigawatt of electrical power. Diablo Canyon was built over 20 years ago, so perhaps some of this costs escalated. But if you just look at the raw cost of building the plant, it's relatively small. About the same cost would be needed to build a gigawatt output thermal power plant. So, you basically would spend roughly $1 per watt of output power, and this output power can be produced 24/7. The nuclear reactor runs at night, the nuclear reactor runs when it's raining. It produces gigawatt of power essentially continuously until the reactor needs to stop and refuel roughly once every few years. So if you look at you take the cost of engineering the reactor, building the reactor, operating the reactor, cost of enriching the fuel, and then disposing of fuel. If you take all of the operating costs that PG&E actually publishes, the costs for producing electricity are somewhere in the neighborhood of 1 to 1.5 cents per kilowatt hour. Now, compared to what you pay for electricity, that's 13 cents per kilowatt hour is what all of us pay to PG&E if we are in the first tier of electrical users, and you pay more if you use more electricity. So the energy is quite cheap. So this is the cost if you, again, amortize the cost of building the plant over roughly 20-year lifespan. Now, of course, this cost does not account for insurance and does not account for potential accidents. So that's the potential disadvantage. The uranium, well, another thing that is important to bring up, you're not burning fossil fuels. The output of the nuclear reactor is steam. In fact, even steam gets recondensed. So inherently, if you capture all of the fission materials and keep them inside the containment dome of the reactor, And then when you extract the spent nuclear fuel, you keep that fuel also in a safe container, and I will show you how safe those containers are. If you keep all of the radiation inside the nuclear reactor, there's no harm to the environment. The output is steam, output is water. In particular, no carbon dioxide, no irritants and pollutants that plague China, which burns a lot of coal. So relatively low environmental impact. But that all assumes that everything goes well and there are no accidents. So you have to balance, if you're again talking about policy, you have to balance the cost and potential advantages of nuclear power against the risk of the accidents. And what happens if the accident actually happens? So when an accident happens, well, the results can be devastating. And again, on our memory, there have been 3 nuclear disasters and nuclear power plants: 3 Mile Island in the US and Pennsylvania, Chernobyl in Ukraine, in Soviet Union, and Fukushima in Japan. So over the last 60 years of nuclear power, roughly, 3 large-scale industrial accidents have happened, Chernobyl being the worst. So from that, you can compute what the risks are and what the environmental impacts are. But the environmental impacts clearly can be devastating to the local economy. Well, both people at the towns near the reactor site would be exposed to radiation. That would cause increases in their cancer rates, if not direct health issues from the acute radiation sickness. And possibly worse is the fact that some of the fission products leave radioactive traces for a long time. Plutonium that's produced has a half-life of 6,000 years, so that's quite a bit, and it's radioactive. Cesium and strontium, 2 of the highly radioactive isotopes producing gamma and beta rays, live for 30 years or so, half-life. So in the case of a nuclear accident where the radiation is allowed to spill into the environment, the impact on the surrounding area can last generations. So that clearly needs to be taken into account on the risk side. The other issue is that, again, the nuclear power is safe as long as you take all of the appropriate precautions, and in particular, it produces no waste into the environment if you contain the nuclear fission materials that are produced in the core. These reactors do produce waste. They produce radioactive isotopes that need to be contained and then stored somewhere. For example, this long-lived plutonium-239 either needs to be reprocessed into fuel, that's what French and Russians do, or US does not allow reprocessing of spent nuclear fuel in the US. And so if you don't reprocess spent nuclear fuel for policy reasons, you have to store it somewhere for tens of thousands of years, since the half-life of this isotope, plutonium-239, is 6,000 years. So you need to keep it somewhere safe, and safe on the scale of thousands of years, which is beyond many generations. So who knows what happens to human race that far in the future, is one of the arguments. And then, of course, you have to transport that waste to a facility where it can be stored safely. So the standard thing to do with this nuclear waste, well, the ideal thing to do, is to bury it underground somewhere and not touch it for tens of thousands of years. This was the proposal solution for the so-called Yucca Mountain nuclear waste disposal site in Nevada, and we'll talk about that a little bit. There is a test nuclear waste storage facility in New Mexico that's operating now, called WIPP, W-I-P-P. It was designed to be effectively a test facility to test a large-scale nuclear storage in Yucca Mountain. So ideally, you would stick the waste, hundreds of thousands of tons, actually, of nuclear waste somewhere underground, close the doors, and not let anybody touch it. But before you do it, you have to transport it. So you have to take the nuclear waste from the reactor that can be somewhere in San Luis Obispo, put it on a truck, drive it to Nevada and stick it underground. So somewhere this nuclear waste would have to be transported on public roads. And that produces safety issues as well. If you actually, so again, I said that the US does not reprocess nuclear fuel, does not allow extraction of plutonium-239, primarily for the reasons that plutonium-239 can be weaponized. Therefore, if you actually produce it on industrial scales for use in other nuclear power plants, you have to worry about plutonium getting in the wrong hands. So this is the issue of plutonium economy. You can design a loop. You can design an economic cycle that takes uranium-238, enriches it, produces enough of the uranium-235, burns it in the reactor, produces plutonium, producing plutonium-239, enriching that plutonium-239 at a reprocessing plant and putting it in another reactor, like Candu reactor, for example. That economic cycle can be designed, but the United States doesn't do that. Other countries do. So where do you store the nuclear waste? Well, ideally, you would want to keep it deep underground so that the bedrock above you or above the site protects humans from exposure to radiation. You also want to stick it underground so nobody finds it accidentally. Let's say in 10,000 years, if you forgot where you dug it, where you put it in, you want to still kind of protect the site. So Yucca Mountain was a site in Nevada. There were actually tunnels dug, relatively shallow mountains. The United States government, Department of Energy, has designed a storage facility to store up to 135,000 tons, metric tons of nuclear spent fuel. Well, you may ask, what's happening with this fuel now? Well, as it turns out, United States does not have this long-term storage facility. At this point, most of the nuclear spent fuel that is produced at nuclear power plants is stored on the sites of those power plants. It's first the nuclear fuel rods are pulled out of the reactor. They still produce a lot of radiation and a lot of heat. They need to be cooled. They're put into the so-called storage pools underwater, and they sit there for a few years, allowing for high radioactivity, low half-life radioactivity to decay away. When it's safe to pull them out of water, when they don't produce enough energy to actually melt those assemblies, the rods are pulled out and put into so-called dry casks. Basically, containers about this big. And those casks sit somewhere on the site of a nuclear power plant, waiting, perhaps, to be transported to underground storage like this, except the United States has canceled the Yucca Mountain project, so therefore there is no place for that material to actually be transported as of yet. And so there are about 200 sites in the US that actually contain spent nuclear fuel, sitting in these dry casks, about 60,000 metric tons spread out over the United States. Personally, I think this presents significantly larger potential dangers than storing everything in one site. You have to secure 200 sites. 157, I think, is the actual number. You have to make sure terrorists, don't get keys to those facilities. They don't try to blow them up, spreading the radiation around like a dirty bomb. So it presents security and safety issues, perhaps, for about 200 communities rather than one. But of course, if the alternative is to build a site somewhere in Nevada in the desert, this is about 100 miles from Las Vegas, near the nuclear weapons testing grounds that were used in the 1960s. So this, would allow all of that fuel to sit in one place, so a single place can be potentially secured. But of course, it has the danger that now, all of Nevada would own the nuclear waste from the entire country, and Nevadans don't like that. Nobody would like this stuff to be in your backyard. And so Harry Reid, the majority leader in the Senate, basically vetoed the whole project. There were statements about dead bodies, or rather over somebody's dead body, that this project would be allowed to proceed. And so it was canceled by the Department of Energy, but this does not cancel the problem. We still have 150 or over 150 sites where the nuclear waste is stored now. Nuclear power plants are still producing waste. And so ultimately, in about 20 years or so, the facilities where this waste is being stored now will run out of room. Something would need to be done in about 20 years, and that's your generation. So your generation will have to make a policy decision about what to do. So you need to be prepared for that. Now I have about 5 minutes. I'll show you how this waste is actually being transported, so you can judge for yourself whether the process is safe or potentially dangerous. Well, nothing can be 100% safe. Accidents happen. So the nuclear waste is stored in these dry casks, which are then put into the containers that can be put on trucks or rail and transported to a nuclear storage facility. Clearly, you don't want an accident on the road with the truck to produce radioactive spill. That would be bad. So these casks, these transport containers that are used to transport the radioactive waste are tested, they're actually rated to withstand all kinds of accidents. Here's a little movie of how these tests are being, or what kind of tests are being done. This is a French movie, so no sound, but United States conducts similar tests. So here's this cask dropped from 20 yards or so, and it has to survive and not leak. So it's basically a big steel container, and then inside the steel container it has little balls that can move around and absorb energy. Here's this thing dropped from 100-yard elevation or so. Some of these containers, they're subjected to fire. They have to withstand several thousand-degree heat. They have to withstand a collision with a wall at 60 miles an hour. And more, and not be damaged. And, other sort of industrial-size school tests are conducted to make sure that the transportation is safe. Again, the Russian facilities and the American and Japanese facilities are tested in a similar way. So these casks are designed to be safe, but still, clearly, communities where the trucks would be passing may worry, perhaps rightly so. Now, the question of whether those worries are founded or unfounded is a judgment call. In some sense, the risk of a nuclear spill, you can protect the trucks from the accidents. You have to secure them so that the nuclear waste is not stolen by terrorists. When you are making policy decisions about whether transporting nuclear waste through towns or through neighborhoods is advisable or not, you sometimes have to compare those risks to other hazards. Here's one. The United States produces roughly 16, let me see what the number is, about 150 million tons of various chemicals. Some of those chemicals can be hazardous. This is a tanker filled with chlorine, with the Capitolium building in the background. Chlorine is a nasty gas, right? Well, we use chlorine as a bleach or to clean surfaces. Chlorine gas used to be used in World War I as a chemical weapon. It kills people. There was an incident with one of these containers derailing in South Carolina, in Gateville, South Carolina, in about 2005. Relatively luckily, unpopulated neighborhood. 9 people died, 350 people were hospitalized with various degrees of chemical burns in their lungs after a relatively small amount of chlorine was spilled from a container that derailed. There are estimates that if such container were to be derailed in Chicago and leak out completely, or in Washington, D.C. in a populated area, tens of thousands of people would die. These estimates vary depending on the rate of dissipation, the wind pattern, and whatnot, but the ranges are typically between 10 and 20,000 people killed if a railroad car like this filled with chlorine would disintegrate, and 30,000 people would be hospitalized. $7 to $10 billion in damage would be made to the community. And there's 150, well, actually, let's see, 13 million metric tons of chlorine being transported on US railroads annually, and 150 million tons of other chemicals. So these are clearly hazards. These hazards are being handled, and there are regulations about safety of this transportation, but somehow the chemical hazards do not receive nearly as much attention publicly than the nuclear hazards, which at least by numbers are, well, the transportation of nuclear spent fuel is in numbers is significantly smaller in volume, mass, and frequency. So again, when you make a policy decision, knowing some of these numbers and their consequences is important. So I will stop here. What we'll do when we come back after the midterm is we'll talk about reactor accidents, and I wish you good luck on Tuesday.